Testing 1, 2. I would like to go over this circuit for those who are probably wondering what the hell I'm thinking with this circuit. So here's what I want to do. I want to channel the paths of the positive and negatives through this circuit every which way possible to explain why each component is where it is. Okay, this diode is here for more than one reason. Stop the positive from shorting out this way to the negative and charging this capacitor continuously. So, and then this diode is also here. Right now in red, you're seeing forward battery voltage from your battery, from your plus to your minus. So we covered this diode, and it's there also to capture the flyback, the negative side. Go back a little bit here. Look at this blue negative sign, how it turns red to a positive. Okay. Okay, and then the diode here will stop the positive from reaching the negative side and wasting energy on this capacitor. And this capacitor is here to create a pulse for this coil in the forward direction. Once this capacitor charges, then the inductor will charge up, and then this capacitor will charge up, and then right, I don't know how to put this, but both these capacitors will charge up and then charge this coil. Okay, so both these capacitors will charge up. The coil will charge up. When the coil is loading off these capacitors, the capacitors will act like an open circuit, kind of disconnecting the coil from the battery and allowing its field to collapse into the reverse polarity through this diode. So that's the second reason why this diode is here, because the positive flyback has to go through that diode. First reason the diode is there to block the forward voltage from going through this way. You want the forward voltage to go through the coil only, and the capacitors, sorry, to create the pulse. So now we covered this diode. Let's cover this diode. So this diode is there to two reasons: to block this positive from flowing through this channel to this negative, and therefore wasting power on this capacitor. So basically these two diodes are blocking this positive from hitting the capacitor in that direction. The channels that you see in green are only for the flyback. You don't want your positive going through this side. So we cover these two diodes. And so if there's no diode here, and if there's no channel here at all, and you remove this channel altogether, then it will still work, I believe. Or wait a minute. No, it won't work, because if the diode's not here, then how does when this positive becomes a negative, how do you get the negative flyback to touch here? You need that there, you see? So that channel has to be there, because then the negative, otherwise this negative flyback won't be able to go here. And this channel needs to be there for the positive flyback. If you remove this capacitor, and it's just a straight connection. If you imagine a straight connection here, no component at all, just these 2 points connected. Well, if you do that, then the positive flyback here and this negative flyback, when it hits the negative terminal here, then this positive flyback will also hit the negative terminal, and it'll kind of like short out the flyback and cancel it. You'll just, you know, you'll just be this, I guess that's how the surge protectors are wired up. You just short out the surge and throw it out in that way. You create a short across it. So that's why the capacitor is there. Because at the time that the flyback's happening, this capacitor is yeah, it's empty and kind of acting like an open circuit. And as soon as the flyback is finished, dumping this way negative and positive this way, which is really fast after your forward pulse. But as soon as it does that, then this happens again, and the capacitors start charging up again. The capacitors don't start charging up until the inductor is fully drained or dumped into dumped this way via the green arrow. Once that is fully completed and the flyback is dumped and this inductor its flyback is removed into the battery, then this inductor will be available to be charged again. And it will, like that. If you don't have this diode here, then the positive will hit the negative right here. You'll just be wasting power. We already went through that. So that's pretty much, I tried to remove some components here to see if it would still operate. And I don't see it happening without both these capacitors here. I tried to, if you just remove this part of the circuit and delete it, it's like an open here, no closing circuit here, but open. Then there's no way to forward charge the coil. You need the capacitor there to kind of act or simulate a switching. Yeah. So these capacitors being 1 microfarad, they're very small capacitance, so it should simulate more of a switch effect and less of a DC smoothing effect. So I don't recommend using large microfarad capacitors here because they'll take longer to drain. And the thing here with radiant energy is to use very little power and a very short duty cycle of a pulse. So by having a 1 microfarad or less, yeah, your frequency will be kind of high, being such a small capacitor. If your high frequency is a problem, you could always lower your voltage, you know. And if you want even a smaller pulse, a weaker pulse, you can go with a nanofarad, picofarad, and then your frequency will go extremely high because you're maintaining your 12 volts here. So you could always drop this down to 2 volts and still it will operate with a lot less, current going through that coil. But the goal here is not to send a lot of current through the coil. The goal here is to just get enough current or voltage needed to push as minimal amount of current as you can through that coil to the other end. So you need a certain amount of voltage to reach the other end of the coil to get through, like pressure, you know? So 2 volts through a 30 ohm coil probably won't go. So you'll have to change that 30 ohms to, like, 5 ohms or something else, Excuse me with the low resolution. But you get my point. You still want to create a very weak pulse, um, because you're not going to get any more amperage by creating a stronger pulse. You're just going to get a higher voltage spike, and I'm not so sure you need to create a higher voltage spike. I just think you need to get your voltage high enough to where it can push through your devices, all your devices, just like pushing through a coil. 2 volts will not go through a 30 ohm coil. It won't make it. No matter how many amps you got, to bring that up to 12 volts to get through a 30 ohm coil. You drop this 30 ohm coil to like 3 ohms, yeah, 2 volts will get through that. And then you could drop your 1 microfarad capacitors to like picofarads or whatever. Or you can keep the 1 microfarads, and your frequency will slow down because you lowered your voltage. If you want to keep a high frequency or tune this to a certain key resonant frequency, well, that's the little math will get you your capacitor rating, and your Henry rating on your inductor. All right, so let's go this over one more time. This diode here is to block the positive from hitting the negative and throwing out power. You want the positive to go through the coil. You don't want it to go through here. So the diode's there for that, and it's also there to capture the flyback, as you can see right here. Without it, you don't capture flyback. Flyback is reverse polarity from your forward polarity. Your forward polarity is in red, and there's your forward polarity. Plus hits here, minus hits here. Reverse polarity, well, this is the flyback. Coil will reverse polarity when it loses its charge. And then it becomes your positive and it has to go through this diode. This becomes your negative and it has to go through this diode. You don't want it going through here, and it won't because that's a positive. And you don't want this positive going through here, and it won't because this is a negative. Um, and it won't also because this capacitor will be empty when this happens. So for this capacitor to act like a short and allow this to go this direction, it needs to be fully charged. And it will go that direction when this is fully charged, but it will go that direction at this time when the coil is empty and acting as a load. Once the coil is fully charged, it's not acting as a load anymore. It can't charge anymore. And these capacitors, when this coil is dumping flyback, these capacitors are they have emptied into the coil already, and the coil now is full. And when the coil's full and the capacitors are full, uh, it's a completed circuit. Now, I may have to add some way to get these capacitors to open circuit again, because once this coil is charged, it's uh, it's full, and it can't be charged anymore. But if the capacitor's still here, it should stay charged. I'm thinking, because it's DC. So I mean, if that happens and these capacitors are not pulsing like they should, uh, they should pulse because once they're fully charged, they're gonna they're gonna charge up this coil, and when this coil fully charges, I believe its impedance raises, so it acts like a higher resistance, and that in turn does not allow the capacitors to stay charged because it needs a load to stay charged. But if the load is not there anymore because the coil is fully charged and it's not acting like a load anymore, you get my point? Then these capacitors don't see a load, and they don't have anything to charge anymore, and therefore they don't have flow either, or they have less flow. So this has never been built, but it's a start to an idea. I'm trying to get away from a transistor somehow and create a switching circuit without transistors, relays, or any other type of switches. I'm trying to use capacitors as switches. I believe Don Smith did that. But see, capacitors typically, they don't switch on and off per se. They just, raise and lower uh, the voltage will fluctuate uh, based on their charge rate. And if you're giving it DC, you could give this system AC to get that pulse you're looking for. If the DC system like this does not create the pulse, once again, this has never been built. In blue up there, it says it's never been built. It's an untested uh, prototype or whatever. Um, so what you could do is instead of feeding this circuit with 12 volts DC, you could feed it AC, whatever voltage AC you want, and there will be your pulse. That will create at least it'll create your oscillation. If not a pulse, if not a DC on and off switch, it'll create an oscillation. And maybe by using AC and certain capacitor ratings, you can effectively create a switch, and you can use capacitor ratings to get your voltage swing from high to zero for that simulated switch. Because if you are able to use capacitors to simulate a high voltage or a low voltage down to a zero voltage using capacitor ratings and circuit design, um, well, that's ideal. That's way better than a transistor. Um, because transistors blow out real easy, and there's no way you're going to blow out capacitor if they're sized correctly to your flyback voltage. So yeah, I just want to throw those thoughts into this circuit here, and that's the whole idea why I'm thinking of doing this, is because I'm trying to because I created a circuit that I found on the internet that was it would take a sine wave, it would cut off the bottom half of the sine wave, and you'd have like an AC pulse on the positive side only, You can, it's called the poor man's desulfator. That same circuit, you can invert it and pulse the bottom half of the sine wave. Too. So that's where I got this idea from. And I know that you can, at least at the very least, with an AC signal, you can cut off half the AC signal and simulate a pulse, but it's not going to be a DC, switch to, high speed switch like a transistor can do. But from that circuit, it tells me that you can change the values of the capacitors to the point where you can reach the zero line by using, or at least very close to the zero line, by using a very, very small capacitance on one end, and then a larger capacitance on your other end for the whatever voltage peak you want to give it, the system. And you could feed the system AC 120 volts, size the capacitors correctly, and it will drop that AC voltage, or it will raise the AC voltage based on your the AC pulse that it. See if I can bring up that circuit. This is the circuit I'm talking about. So there's your AC coming in. That's just to turn it on or off. That's not for pulsing. So this here controls your amperage, and this here controls your voltage. And with this circuit, you can increase the microfarads on this section to lower your voltage. And when you do that, your amperage is going to drop because you have less voltage to push your current amperage through. So you can increase this capacitor to bring your amperage back up after you lower your voltage here. So here's an example of how you can use capacitors to to change the voltage and the amperage. You can do that with this circuit here, and out comes a DC pulse because it's really half of the AC sine wave coming out, the top half, and that's why it's called DC, because it's not plus and minus coming out. Rectifier does that. It cuts the bottom half of the sine wave, leaves you only the top, and it becomes DC. So you could use this type of circuit here, mess around with these caps. If you have a very low capacitor here in microfarads, it would be very low amperage. And, supposing you use picofarad capacitors here or 1 microfarad capacitors, and you lower your AC signal. So, what if they're 1 kilovolt, AC capacitors? Then you don't need to lower your AC 120 volts. But if you use 1 kilovolt AC 1 microfarad capacitors here, you're not going to drop your voltage at all. In fact, the voltage is going to go way high. To drop the voltage here, you need to increase the microfarads, not decrease it. But the amperage here will probably blow out the 1 microfarad capacitors because they're only rated for, I don't know, a couple watts. So then you would have to change this guy here down to a probably a 1 microfarad capacitor, 1 kilovolt AC. And then you would have a, a very weak, very fast rise and fall time DC pulse. It would probably look less. It would look less like the top half of an AC sine wave, and probably more like closer to the spike that we get from a transistor switching inductor. So that's what I wanted to mention here. This is very similar, although there's an inductor here. Just food for thought, guys. Over and out.